Two particles separated by 14 billion light years. One changes, the other responds instantly, not at light speed, but instantaneously. No signal travels between them, no force connects them, yet somehow, impossibly, they remain connected. This isn't science fiction, it's quantum entanglement, and it's happening right now, throughout every corner of our universe. Einstein called it spooky action at a distance and spent decades trying to prove it couldn't exist. He failed. The universe, it seems, operates by rules that defy our deepest intuitions about reality itself. What if the space between objects isn't really space at all? What if distance is an illusion, and everything in the universe remains fundamentally connected in ways we're only beginning to understand? Today, we journey through evidence that challenges everything we thought we knew about the fabric of reality. Prepare yourselves. We begin. In 1935, Albert Einstein was furious. A paper had just been published describing a quantum mechanical prediction so absurd, so contrary to physical law, that Einstein was certain it exposed a fatal flaw in quantum theory itself. Working with colleagues Boris Podolsky and Nathan Rosen, Einstein crafted what he believed was the death blow to quantum mechanics. The paper described two particles that interact and then separate. According to quantum mechanics, these particles would remain connected, their properties correlated, no matter how far apart they traveled. Measure one particle, and you'd instantly know something about the other, even if it was on the opposite side of the universe. Einstein's argument was simple. This was impossible. Information cannot travel faster than light. That was the bedrock of his theory of relativity, perhaps the most successful theory in all of physics. If quantum mechanics predicted instantaneous connections across space, then quantum mechanics must be incomplete. He called it a paradox. Today, we call it quantum entanglement. To understand why Einstein was so disturbed, imagine two coins. You flip them both, put them in separate boxes, and send one box to Mars. According to normal logic, each coin is either heads or tails from the moment you flipped it. Opening the box on Earth doesn't change what's inside the box on Mars. But quantum mechanics says something different. It says that until you open a box and look, each coin exists in a state called superposition, simultaneously heads and tails. The act of measurement forces the coin to choose one outcome. Here's where it gets strange. If these coins are quantum entangled, the moment you open the box on Earth and see heads, the box on Mars instantaneously contains tails. Not because a signal traveled between them, not because they were predetermined to be opposite, but because measuring one particle collapses the quantum state of both particles simultaneously. Einstein believed this violated the principle of locality, the idea that objects can only be influenced by their immediate surroundings. He argued that the particles must have predetermined properties all along, what physicists call hidden variables. The quantum connection, he insisted, was just an illusion created by incomplete information. For 30 years, this remains a philosophical debate. Quantum mechanics made accurate predictions, but no one could test whether Einstein's hidden variables existed or whether reality truly was as weird as quantum theory suggested. Then, in 1964, a physicist named John Stuart Bell changed everything. Working at CERN during his spare time, Bell developed a mathematical theorem that could distinguish between Einstein's hidden variable theory and genuine quantum entanglement. Bell's theorem showed that if hidden variables existed, certain measurements on entangled particles would produce results within specific limits, what became known as Bell's inequality. But if quantum mechanics was correct, if entanglement was real, the measurements would violate Bell's inequality in precise, predictable ways. For the first time, Einstein's spooky action at a distance could be tested. The first experimental tests came in the 1970s and early 1980s. Physicists at UC Berkeley, Harvard, and the Institut d'Optique in Paris began creating pairs of entangled photons and measuring their properties. The results were unambiguous. Bell's inequality was violated. Again and again, the measurements matched quantum mechanics predictions perfectly. Einstein's hidden variables didn't exist. The entanglement was real. In 1982, physicist Alain Aspect conducted the definitive experiment at the University of Paris. He created pairs of entangled photons and sent them flying in opposite directions to detectors 13 meters apart. The measurement settings at each detector were changed so rapidly, in just billionths of a second, that no signal, not even light, could travel between them in time to coordinate their results. The photons remained correlated, perfectly, instantaneously. The universe, it appeared, really did allow for instantaneous connections across space. Reality was stranger than Einstein ever imagined. But this represents just one piece of a much larger puzzle, because quantum entanglement isn't limited to laboratory experiments with carefully prepared photons. It operates throughout the universe, at scales from the subatomic to the cosmic. The evidence forces us to confront an uncomfortable possibility that the space separating objects might not be fundamental at all, but rather an emergent property arising from something deeper, something that binds every particle in the universe together in ways we're only beginning to comprehend. In 2012, physicists at the University of Vienna achieved something remarkable. They entangled two photons, then sent one to a receiving station 143 kilometers away, not through fiber optic cables, but through the air, across the ground. The distance was equivalent to orbiting altitude for satellites. The entanglement persisted. The particles remained connected across a distance where Earth's curvature becomes visible, where the atmosphere begins to thin, where traditional notions of connection seem absurd. Yet measure one photon, and its partner instantly reflected that measurement, as if 143 kilometers of space simply didn't exist. But this was merely the beginning. In 2017, China launched the Micius satellite, named after an ancient Chinese philosopher. Its mission was unprecedented, to test quantum entanglement, not across kilometers, but across space itself. The satellite generated pairs of entangled photons and beamed them down to ground stations 1,200 kilometers apart, one in Delinga, the other in Lijiang. The photons traveled through the vacuum of space, through Earth's atmosphere, through regions of intense radiation and magnetic fields. They remained entangled. Scientists measured the correlation between the photons and found it violated Bell's inequality by 10 standard deviations. In statistical terms, this means the probability that the correlation occurred by chance was less than 1 in several trillion. The quantum connection persisted across a distance greater than the width of France and Germany combined. The space between the particles had no effect whatsoever on their instantaneous correlation. What scientists discovered next would challenge our understanding even further. Researchers at the Institute for Quantum Optics and Quantum Information in Vienna conducted an experiment that sounds like science fiction. They entangled two photons, then sent one through an optical fiber while simultaneously changing the measurement basis at the detector faster than light could travel the distance. The measurement choice was made after the photon was already en route, after the point where any signal, even traveling at light speed, could have reached it. The photons still showed perfect correlation. This phenomenon, called delayed choice, suggests something profound. The entangled particles don't just share information instantaneously. They seem to exist in a state where concepts like before and after don't apply in the way we intuitively understand them. But the evidence extends far beyond photons. In 2009, researchers at the National Institute of Standards and Technology in Boulder, Colorado, successfully entangled two atomic ions, electrically charged atoms separated by a distance of 1 meter. Unlike photons, which are massless particles of light, atomic ions have substantial mass. They're matter. They can be held in place, manipulated, and measured with extraordinary precision. The fact that matter itself can be entangled means this isn't just some quirk of light. It's a fundamental property of physical reality. By 2011, scientists had entangled diamonds, actual macroscopic objects visible to the naked eye. Researchers at the University of Oxford created entanglements between the vibrational states of two 3-millimeter diamond crystals, each containing trillions of atoms. For 50 picoseconds, these diamonds existed in an entangled state. Their quantum properties correlated across space, despite their macroscopic size. The most remarkable discovery involved entanglement in time. In 2013, physicists at the Hebrew University of Jerusalem demonstrated what they called quantum entanglement in time. They created entangled photons, but with a twist. The two photons never existed simultaneously. They measured and destroyed the first photon. Then, afterward, they created the second photon and found it was still entangled with the first, with a particle that no longer existed. The quantum correlation persisted across time itself, suggesting that entanglement transcends not just space, but temporal separation. Particles that never coexist in time can still be fundamentally connected. This represents just one piece of a much larger puzzle hidden in the quantum structure of the universe. In 2019, scientists at the University of Glasgow made a discovery that sent shock waves through the physics community. They managed to photograph quantum entanglement directly, capturing an image of two photons interacting and violating Bell's inequality in real time. The image showed something that shouldn't be visible: the quantum correlation between particles frozen in a photograph. For the first time, we could see the supposedly invisible connection that Einstein denied could exist. But here's what makes this discovery truly unsettling. The image reveals that entanglement isn't some abstract mathematical property. It's a physical phenomenon that manifests in measurable, observable ways. The correlation appears in the pattern of phase relationships between the photons, a pattern that classical physics says should not exist. The implications get stranger when we consider the cosmic microwave background, the afterglow of the Big Bang that fills all of space. In 2015, theoretical physicists at MIT and the University of Maryland published calculations suggesting that entanglement might be woven into the very fabric of spacetime itself. Their work, extending earlier theories by physicists Mark van Ramsdonk and Brian Swingle, proposed that the geometry of space, the three-dimensional arena in which we live, might actually emerge from quantum entanglement. Think about that. Space itself might not be fundamental. The distance between objects, the geometry that seems so real and tangible, could be a consequence of quantum entanglement between the fundamental building blocks of reality. In this view, when particles become entangled, they don't just share a quantum connection across space, they literally create space through that entanglement. This theory makes testable predictions. If space-time emerges from entanglement, then disrupting the entanglement should affect the geometry of space itself. In 2017, physicists at Caltech and MIT conducted experiments inspired by this idea, using quantum systems called tensor networks. These simplified models of quantum entanglement showed that removing connections between entangled particles caused the space in the model to tear apart, creating disconnected regions. The mathematics matched exactly with Einstein's general relativity, the theory that describes how mass and energy curve spacetime. Entanglement and gravity might be two sides of the same coin. Recent observations have revealed something even more profound. In 2020, researchers analyzing data from the LIGO gravitational wave detectors discovered quantum entanglement in objects weighing 40 kilograms. The mirrors in LIGO's interferometer arms, each the size of a human torso. These weren't microscopic particles in a controlled laboratory. These were massive objects, vibrating with thermal energy, yet still exhibiting quantum entanglement in their motion. The boundary between quantum world and the classical world, it seems, is far less distinct than we imagined. But perhaps the most disturbing evidence comes from black hole physics. Stephen Hawking's calculations in the 1970s showed that black holes emit radiation, now called Hawking radiation, due to quantum effects near the Entanglement. This radiation is thermal, seemingly random, carrying no information about what fell into the black hole. But this creates a paradox. Quantum mechanics says information cannot be destroyed. If a black hole evaporates completely through Hawking radiation, where does the information go? In 2013, physicists Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully proposed a shocking solution. The event horizon of a black hole might be a firewall of intense energy created by the breakdown of quantum entanglement. Their argument goes like this. The Hawking radiation particles are entangled with particles falling into the black hole, but those particles are also entangled with particles inside the black hole. Quantum mechanics says a particle can't be maximally entangled with two different partners. That's called the monogamy of entanglement. Something has to break. And when it does, the energy release would be catastrophic, a wall of fire at the black hole's boundary. The evidence extends beyond black holes into the realm of the very early universe itself. Cosmologists studying the cosmic microwave background have found patterns that suggest quantum entanglement might have existed on cosmic scales just after the Big Bang. These patterns, tiny temperature fluctuations spread across the sky, appear to be correlated in ways that suggest they originated from quantum fluctuations that were once entangled. As the universe expanded, these entangled regions were stretched to astronomical distances, yet the correlation remained imprinted in the cosmic background radiation. We are quite literally surrounded by evidence of ancient quantum entanglement on the largest scales imaginable. In 2009, physicist Mark von Ramsdonk at the University of British Columbia published a paper that would transform our understanding of reality. The title was technical, Building Up Space-Time with Quantum Entanglement, but the implications were revolutionary. Van Ramsdonk proved mathematically that in certain theoretical universes, space-time is literally constructed from quantum entanglement. In his models, if you removed the entanglements between regions, space itself would tear apart, fragmenting into disconnected pieces. The geometry of space, the three dimensions we move through, the distance between objects, the arena of all physical reality, emerged from the patterns of quantum entanglement between fundamental particles. This wasn't philosophy, it was rigorous mathematical physics, grounded in string theory and quantum field theory. The theory that ties everything together is called ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind in 2013. The name references two famous papers, ER for Einstein and Rosen's 1935 paper describing wormholes, Einstein-Rosen bridges, and EPR for Einstein, Podolsky, and Rosen's paper on quantum entanglement. The proposal is stunning in its simplicity. Quantum entanglement and wormholes are the same thing. When two particles become entangled, they're actually connected by a microscopic wormhole, a tunnel through space-time. The spooky action at a distance that Einstein found so troubling isn't action across space. It's connection through space, through a geometric shortcut in the fabric of reality itself. The wormholes are far too small to send information or matter through. They're quantum-scale phenomena, but their existence provides a geometric interpretation of entanglement that resolves many paradoxes. Leonard Susskind, one of the founders of string theory and a professor at Stanford University, describes it this way. Entanglements is the connective tissue of space. Without it, space would fragment into isolated points. The smooth, continuous geometry we experience emerges from a vast network of quantum entanglement connecting every region to every other region. This forces us to reconsider fundamental assumptions about the nature of distance and separation. When you look at a distant star, you think of empty space between you and that star. But according to ER equals EPR, that space might be more accurately described as a dense network of microscopic wormholes, quantum entanglement, creating the illusion of smooth, empty distance. You're not separate from that star in the way you think you are. You're connected to it through the quantum structure of space-time itself. Competing interpretations exist, of course. Some physicists argue that entanglement doesn't create space, but rather reflects deeper laws we don't yet understand. Others suggest that space might be fundamental after all, with entanglement as a property that exists within space rather than creating it. But the mathematical evidence increasingly points towards space-time emergence. The equations of general relativity can be derived from quantum entanglement in certain models. Gravity, the curvature of space-time, appears to be an entropic force arising from changes in entanglement. As physicist Brian Swingle at the University of Maryland puts it, entanglement is the fundamental thing, and space is derived from it. Recent breakthroughs suggest we're on the verge of harnessing quantum entanglement in unprecedented ways. In 2020, China achieved quantum teleportation across 44 kilometers using the Micius satellite. They didn't teleport matter, that remains science fiction, but they teleported quantum information, the quantum state of a photon, using entanglement as the carrier. The implications are staggering. Quantum teleportation could enable perfectly secure communication, immune to eavesdropping. The European Space Agency is already developing its own quantum communication satellite scheduled to launch in the late 2020s. By 2030, scientists predict we'll have a global quantum internet with entangled particles serving as unhackable communication channels between continents. But the most profound implications involve computing. Google's Sycamore quantum processor, announced in 2019, achieved quantum supremacy, performing a calculation in 200 seconds that would take the world's most powerful supercomputer 10,000 years. The processor used 53 qubits, quantum bits, that maintain entanglement with each other. As quantum computers scale to hundreds or thousands of qubits, they'll exploit entanglement to solve problems that are fundamentally impossible for classical computers. Drug design, cryptography, optimization problems, climate modeling, entire fields will be transformed. IBM, Intel, Microsoft, and dozens of startups are racing to build large-scale quantum computers. The breakthrough could come within this decade. Ongoing research aims to test entanglement at ever larger scales. The International Space Station may soon host experiments testing quantum entanglement in microgravity, measuring how Earth's gravitational field affects quantum correlations. Proposed missions would place entangled atomic clocks on satellites, using quantum correlations to test whether gravity and quantum mechanics can be unified. Any deviation from predicted entanglement could reveal new physics, perhaps the first glimpse of quantum gravity. Other researchers are working on quantum sensing, using entangled particles to detect gravitational waves, dark matter, or even dark energy. Entanglement makes measurements more precise than any classical technique, potentially revealing phenomena we've never observed. What this means for us, for humanity, extends beyond technology. If space truly emerges from entanglement, then the universe is fundamentally non-local. Separation is an illusion. Every particle that interacted in the early universe remains connected through quantum correlations that survive across billions of light years. You are made of atoms forged in stars, atoms that were once part of the hot, dense plasma of the early universe. Those atoms were entangled with others, scattered across the cosmos. In a very real sense, you remain connected to distant corners of the universe through quantum correlations that have persisted for 13.8 billion years. And if consciousness involves quantum processes, still a controversial idea, then entanglement might play a role in subjective experience itself. Some physicists, like Roger Penrose at Oxford, have proposed that consciousness arises from quantum computations in brain structures called microtubules. If true, then the experience of being a unified self, of having a single, coherent awareness, might emerge from quantum entanglements between neurons or cellular structures. We would be, quite literally, held together by the same quantum phenomenon that binds the universe. The most profound implications emerge when we consider what quantum entanglement suggests about the nature of reality itself. In the standard interpretation, measuring an entangled particle instantaneously affects its partner. But instantaneously implies an objective notion of time, a universal now that determines when events occur. Relativity tells us there is no such thing. Time is relative. Events that are simultaneous in one reference frame occur at different times in another frame, moving relative to the first. So when does the entangled partner know it's been measured? The answer suggests something radical. Perhaps the universe doesn't have a single objective timeline. Perhaps reality is more like a network of correlations, with the appearance of sequential time emerging from our limited perspective within that network. Physicist Carlo Rovelli at Aix-Marseille University has developed a theory called relational quantum mechanics that takes this idea seriously. In his view, quantum states don't have absolute properties. They only have properties relative to other systems. When you measure an entangled particle, it doesn't have a definite state from the perspective of the universe as a whole. It only has a definite state relative to you, to your measuring apparatus, to your brain in registering the result. From another observer's perspective, the particle might still be in superposition. Reality, in this view, is observer-dependent all the way down. This doesn't mean reality is subjective or that you can change facts by thinking about them. It means the universe doesn't have a single God's eye view perspective. Reality consists of the relationships and correlations between things, not the intrinsic properties of things themselves. What the evidence suggests about reality itself may be even stranger. Some physicists, including Nobel laureate Gerard Tofte, have proposed that our three-dimensional universe might be a hologram, a projection from information encoded on a two-dimensional boundary. This holographic principle emerged from black hole physics, but has profound connections to entanglement. In holographic models, the entanglement between regions of space corresponds precisely to the geometry connecting those regions. The universe is information. The physical world, matter, energy, space, time, emerges from the pattern of quantum information and its entanglements. You're not a collection of particles in space. You are a pattern of quantum information embedded in a network of entanglement that connects you to everything else that exists. Perhaps the deepest mystery involves what physicists call quantum non-locality. When particles are entangled, they're correlated in ways that violate Bell's inequality, ways that are impossible for any local theory to explain. The correlations are stronger than anything classical physics allows, yet they don't permit faster-than-light communication. Why? Why does the universe allow these impossible correlations, yet still prohibit sending messages faster than light? The answer might involve the fundamental structure of causality itself. Physicist Lucian Hardy showed that if you could use entanglement to send signals faster than light, you could create causal paradoxes, effects preceding their causes. The universe seems to be carefully balanced at the edge, maximally non-local, allowing the strongest possible quantum correlations, while still prohibiting causality violations. It's as if the universe is designed to be as strange as possible while remaining logically consistent. The most profound implication is this: the universe may not be made of things. It may be made of connections. Particles, fields, even space and time may be emergent phenomena arising from a deeper level of reality consisting purely of relationships and correlations. Quantum entanglement would then be the most fundamental feature of existence, more fundamental than matter, more fundamental than energy, more fundamental than space-time itself. Einstein spent 30 years fighting against this conclusion. In the end, the universe proved him wrong. Reality is far stranger, far more interconnected, far more unified than classical physics ever imagined, and we're only beginning to understand what that means. We began with two particles separated by impossible distances, instantaneously correlated across the void. We've journeyed through evidence from laboratory experiments to satellite missions, from diamond crystals to black hole firewalls, from the cosmic microwave background to the quantum structure of space-time itself. The picture that emerges is breathtaking. We live in a universe where distance is an illusion, where separation is not fundamental, where the space between objects emerges from the quantum connections that bind everything together. The current scientific consensus is clear. Quantum entanglement is real. It violates Bell's inequality. It persists across arbitrary distances, and it may be the fundamental substrate from which reality itself is woven. What remains unknown is perhaps more exciting than what we've discovered. We don't yet know if entanglement plays a role in consciousness, in the origin of life, in the arrow of time that distinguishes past from future. We don't know if the entanglement that connects particles across the universe is the same phenomenon that creates the experience of now, the felt sense of existing in a single present moment. We don't know if we'll ever harness entanglement to probe the deepest mysteries: dark matter, dark energy, the quantum nature of gravity itself. But we do know this: the universe is not a collection of separate things occupying separate places. It is a unified whole, bound together by connections that transcend space and time. You are part of that whole. Every atom in your body was once entangled with atoms now scattered across the cosmos. In ways we're only beginning to understand, you remain connected to them, connected to the stars, to distant galaxies, to the very fabric of existence. Einstein called it spooky. Today, we call it reality. The universe is vast. The mysteries are endless. The journey continues.